In this video, we're going to attempt to better explain what it means when we talk about closure. And no, we're not just talking about the end of a bad relationship where you need closure. We're actually talking about the mathematical idea of closure. So, a set is closed under an operation if applying that operation to two elements in the set produces another element in the set. So a question that we're going to ask quite a bit in here is blank, where this will represent a set, closed under, and we're going to give some sort of operation here. Operation. Now, this can be a tricky thing to prove, because if we want to prove that it's true, we're going to need to prove this using generic elements. Closure under an operation applies to everything within the set. So if we want to prove that it is closed under an operation, then we need to prove that it's true for everything within the set. If not, then it'll be our responsibility to provide one counterexample. So if the answer is no, we need to provide one counterexample. Now that can be a rather daunting task. So let's try out a couple of examples. Is the set of odd integers closed under addition? Is the set of odd integers closed under addition? So what we're really asking here is, if I take an odd number and I add to it another odd number, will the result always be an odd number? And the answer to this is absolutely not. You can take any odd number and add to it any other odd number, and you are actually guaranteed to wind up with an even number. So we can say, therefore, the set of odd integers is not closed under addition. Set of odd integers is not closed under addition. However, we could also switch it up a little bit, pose a similar question. Is the set of even integers closed under addition? So this is posing the question, if I take an even integer plus another even integer, is it always going to be another even integer? I'll let you pause the video if you'd like to contemplate that for just a moment. However, once you unpause, we're going to go ahead and say, yes, it is always true that if you add an even integer to an even integer, that you will wind up with an even integer. Well, we're going to have to deal with two generic elements, as generic as we can get. So the definition of even is that it is divisible by 2. So x is even if we can express it in terms of 2 times an integer. So, for example, y is 6 even? Well, because that would be 2 times 3, and 3 is an integer. Y is 16 even? Well, because it's 2 times 8, where 8 is an integer. So what we're going to do is let x and y be even integers. Then x is going to be equal to 2 times m, where m is an integer, and y is going to be equal to 2 times, well, I've already used m, so let's use something near it in the alphabet, 2n, where n is an, oh boy, integer. We're going to make it fit. Okay, good. Now, to prove closure, we want to take x plus y and prove that this result is going to be even as well. So we just said x is equal to 2 times m. We said y is equal to 2 times n. I want to prove that this is equal to 2 times some integer. Well, if we factor out the common factor of 2, and then use the fact that an integer plus another integer is guaranteed to give us another integer, that's because the integers are closed under addition. Oh, integer. There we go. That looks much better. We can now say that this is even. Therefore, the even integers are closed under addition. Now, the last two examples that we've looked at are very particular in the sense that the first one can never be true, and this one is always true. What about operations that are sometimes true? Is the set of rational numbers closed under the operation of exponentiation, which is a fancy way of saying if I take a rational number and I raise it to the power of a rational number, is the result guaranteed to be rational? Now, rational simply means that it can be expressed in terms of a fraction as an integer over an integer. So a couple of examples, I could take 2 raised to the third power. That would be 8, which is valid. That's a rational number to a rational power. We get a rational number out of it. I could also take 4/5 and raise it to the second power. We get 16 over 25, which is, again, a rational number. Now, ultimately, it does not matter how many times you show that it's true. The only thing that you would need is one single counterexample in order to show that this is false. Well, 2 is a rational number. 1/2 is a rational number as well. However, 2 raised to the 1/2 power is the square root of 2, which is irrational. It does not matter how many times you demonstrate that something is true. It only takes one counterexample to disprove what we call this universal statement. Universal statement is something that is always true. Therefore, the set of rational numbers is not closed under exponentiation. Set of rational numbers is not closed under exponentiation. So again, it doesn't matter how many times you prove that it does work, it only needs to not work one single time in order to disprove the statement.